I'm Paul Gregg. I'm taking a break from my normal backyard roller coaster videos to check out an air cannon, which I looked at a bunch of videos. You can see how to make this. I won't tell you how to make it. There's plenty of them out there. But basically the parts are that there's a 4-inch PVC Schedule 40 pressure chamber, and then I've got a little pressure gauge here and a Schrader valve where you can put air in, pressurize it. And then this is a modified sprinkler valve where if you release the small pressure in the valve, then all this air can dump really quickly into the barrel here. I'm using green dot tennis balls, which are different pressure than regular tennis balls. It's a pretty tight fit in there. If you want to get in there, one trouble with PVC pipe is the outer diameter is controlled very tightly during the extrusion process so that you can bond them into these fittings. And so when you control one side of something really tightly, the inside diameter suffers a little bit, and the outside diameter of a PVC pipe is controlled within 5 thousandths, plus or minus 5 thousandths of an inch. The inside diameter is plus or minus 15 thousandths of an inch. So it kind of goes all over the place. So you don't really know what you've got on inside diameter. So if you buy a pipe at one store, you buy a pipe from a different lot at a different store, they'll be the different inner diameters. So you got to be careful of that. And maybe I got a small one, but it works fairly well. You want these tennis balls to have a little bit of friction so that it uses all the pressure the way you want it to. But if it had too much friction, that would be a lot of drag and take away from the performance of it. So you slide the ball down to the bottom, and then you pressurize it. We'll talk about safety, and I'm going to go to the computer and talk a lot. I've written on here minimum burst pressure 710 psi. That's the burst pressure of a 4-inch Schedule 40 PVC pipe. The maximum the suggested operating pressure is more like 200 psi. There's a lot of factor of safety built in there, but it gives you a good feeling that my compressor only goes to 125 psi. This is 710 psi. That seems like a lot of margin over 5 times the capability here is what I can put into it. So now that will change a lot with temperature. I'll talk about that a little later in the video. So the way you run these things is you've got the ball in there, you pressurize this, and I'm watching the gauge here. I'm going to go up to about 70 psi. Well, maybe 80. Okay. Now we take it outside and we release this low pressure side of this vent. This discharges fairly quickly. It's a 1-inch valve. We're going to go out in the yard and we'll shoot it up in the air. All right. So I'm going to go through some of the engineering that pertains to the air cannon I built. I'll try to do this fairly quickly and not get off track and make it too boring. If you were just interested in watching the video, I encourage you to stick around and see how an engineer would approach whether you can make an air cannon that's safe or not, and what you should and shouldn't do with it. So this is my air cannon. There's a lot of online variations of how to build a PVC air cannon, and so I won't go through that. The one I found was by Stephen Wassel on YouTube, which seems fairly simple. Has the pressure chamber has reducer fittings that go to from a 4-inch pressure chamber to a 1-inch pipe through a modified sprinkler valve, and then he had 4 different barrels he could screw on there and try different projectiles. I'm going with the 2.5-inch because I want to shoot tennis balls. I did find another at grabcad.com, which is a library of computer-aided design models, and I imported this into my Autodesk Fusion 360 computer-aided design program. and this is the way it came in. His barrel's fairly short, I found out, so I modified a few things. But basically, you've got the two end caps. This one doesn't use the reducers, so it was a little cheaper, and I went this way, but I kind of wish I hadn't. What this guy did, a user named Bale, put this into GrabCAD. So he drilled holes in these two end caps and threaded PVC threaded fittings in there. The end caps really aren't, they're about 1/4 inch thick or something. That's not really thick enough to grab more than 4 or 5 threads, which is probably not enough. And I wish I'd gone with the reducers. I may redo this whole thing. Wouldn't be too hard to redo those parts. 1-inch sprinkler valve, little air nozzle valve for releasing the pressure. There's a small diaphragm in here. Once it's released, the main pressure can gush through from the chamber to the barrel. My projectiles are the green dot youth tennis balls. They have lower pressure than adult tennis balls, so they'll fit into this 2.5-inch barrel fairly snugly. So the first question is, how is this the right barrel length, and this is the right chamber length, pressure chamber. So I could have, you could do a lot of gas law calculation and get here, but there's a lot of kind of unknowns. What's the friction of the ball in the barrel, and how fast can the air really flow through the valve itself? So there's a lot of things you don't know about this that would need some testing or real deep fluid flow analysis. But luckily, some people at spudfiles.com have done all this work in an empirical way, which means they tested this. They made a bunch of air cannons of different size chamber and barrels, and they measured the velocity as the projectile comes out of the barrel, and they came up with this chart which says basically the volume of the compression chamber divided by the barrel volume. If you get that within about 0.6 to 0.8, so in other words, if the barrel was 100 cubic inches, then if you get the chamber about 70 cubic inches, then you're in kind of a sweet spot, and that's where you're going to get the best performance. Now, if you're out here, this is where the chamber is very big, and you're kind of wasting compressed air out here, but you do get a big bang out of it for what that's worth. Down in here, your chamber would be very small compared to the barrel, and you could get a situation where the ball wouldn't even reach the end of your barrel. It would accelerate and then start to slow down and come to a stop somewhere if the barrel was really long. So this is a sweet spot. We know this. It's empirically derived, and all you have to do is know the volume of a cylinder, which is this little formula, and you can come up with a fairly optimum design. That's what I did. I kept the 10-inch pressure chamber. I had a bigger piece of 4-inch PVC, and I started off with a bigger pressure chamber, but the barrel had to get really long, like 96 inches long or something, and I didn't want to carry that around, so I did a 10-inch pressure chamber and a 36-inch barrel, and that is right in this 0.7 C to CB ratio. So that was fortunate. So this is the next thing I did was try to identify, when any engineer looks at a structural engineer looks at a design, you want to identify the potential structural failure modes. What could happen? What could go on here? All of these cylinders could burst. The 2.5-inch cylinder, the 1-inch pipes, the 4-inch cylinder especially is going to be something we want to look at, because the stresses are higher in a larger radius cylinder. The spherical end caps, are they going to crack and burst? the fitting where it threads in there in the high pressure area. Are the bonds good in the joints? What's this pressure? What's this sprinkler valve rated for pressure? Is anybody blown up? I wasn't able to find anybody who'd actually pressurized a sprinkler valve to burst, but they say it's capable of 120 psi. Now it may be that the rubber diaphragm in here doesn't work if you go to higher pressures than that, and so that wouldn't be good. So luckily my as I said, my compressor only goes to 125 psi, and so that's my limit anyway. And so I'm unable to do much detailed analysis on these little parts here, but as long as I know they can take 120 psi very reliably, then I feel pretty good about it. One other, there's lots of things that could happen. You know, this is what you do. I work on aerospace vehicles, airplanes, rockets, and stuff like that. And you're always thinking about what's the worst thing that could happen to this. So that's your load cases. And for one of these, I mean, what if I drop the gun, I pressurize the chamber, I drop it on a rock on a cold day when the PVC is more susceptible to fracture? This whole thing might just explode on me. So there's lots of obscure load cases that you have to think about. I'm unable to really analyze that very well. I guess I could freeze the gun and pressurize it and drop it, but I want to do that from a safe distance. That would be a good way to test it. So component-wise, we have the Schrader valve, we have the pressure gauge I can look at when we're pressurizing, and so I've identified a bunch of failure modes. I won't go into the analysis of all of these failure modes, but just some that are more interesting. So that there's a pretty easy formula for the stress in a cylindrical pressure vessel and a spherical one. Turns out the axial stress would be in this direction. So the crack would form in the circumferential direction, and the axial stress is equal to the pressure times the radius divided by 2 divided by the thickness. And that's also the spherical stress out here in the domes. And so we're not too concerned about. The reason being is that the hoop stress is, and these are formulas you can derive fairly easily if you just look at free body diagram, but I won't go into that. I could do it, but these are fairly simple formulas. That's why it's nice to show them in a video like this, where it's kind of an introduction to the engineering. The hoop stress is twice as much as the axial stress. It's pressure times radius divided by thickness. And so pretty much I'm sure that the hoop stress in this direction is going to cause it to crack in the longitudinal direction, and that's probably what I ought to be looking at. And I could look at it in this 4-inch one, which is a certain thickness, this 1-inch one, which has a smaller radius but a bigger thickness, and the barrel itself, where the radius is a medium, its diameter is 2.5 inches, and the thickness is what it is. So I have all that information, and I'll check pretty easy to check the margin on those 3 cases. The pressure is certainly highest in the pressure chamber. After it goes through here, I don't really know what the pressure is in the 1-inch and 2.5-inch barrels. And so I can just, to be safe, I could assume that it's a full 125 psi. It's not, but just to be safe, and we'll see how it comes out. Now you look at this formula, stress in the hoop direction is equal to pressure. Well, first, let's say this is what we're doing up here. We're seeing what the calculated or applied stress is, and that's little f. Normally it's sigma, but at Boeing we use f for some reason. So the little f would be the applied stress that I calculate using this formula. F is the allowable stress, or the strength, and I get that from online, someone who's documented the yield strength of PVC. And what I need is for the strength to be a lot higher than the calculated stress. And then I know I'm good. I can have a positive margin, is what we say. And I'll show you how to calculate margins. It's pretty simple.
So stress in the hoop direction is the pressure times the radius divided by thickness. Now, a lot of engineering is looking at these formulas and saying, what does this really mean? I got to feel for what this equation is doing. And you'll notice as the stress increases linearly, which means it makes a straight line if you plot it, with higher pressure. So if I double the pressure, I double the stress. And same with the radius. If I increase the radius, so if I go from this 1 inch to this 4-inch one, I know my stress in the PVC plastic in the hoop direction is going to be 4 times as much. And that's why intuitively I know that looking at the unless the thickness is 1/4, then the thickness of the 1-inch pipe is 1/4 of the thickness of the 4-inch pipe. They would be even in that respect, but I know that the thickness of the 1-inch pipe is not, it's bigger than 1/4 of the thickness of the 4-inch pipe, and so I know this is going to be critical out here. And we'll check it on the 2.5-inch pipe too to see it. Now thickness is different because as the thickness, if you know the numerator, denominator, as the thickness gets bigger, this number over here, the hoop stress, is going to get lower. And that makes sense. The thicker I make the pipe, the lower the stress is, because the load can be distributed over more material. And so this chart says that as the thickness goes up, the stress goes down, whereas if the pressure and the radius go up, the stress goes up. Now, those are linear ones. Most times in the world, things are nonlinear, in which case there'd be some kind of an exponential term, an r squared or a t squared or something like that, and you get lines that weren't linear, and you just have to do that. But it's harder, it's easy with this formula because if I double the thickness, then I have the stress. So it's easy to see that way. But if I'd have to do some calculating to figure that out if it was a nonlinear relationship. So this is the first failure mode we'll look at. This is hoop stress. I put 125 psi in here, and in order for this crack to appear in the axial direction, which is 90 degrees to the load direction, I can calculate this pretty easy. 125 psi times the radius, 2.25 inches, divided by the thickness, which is 0.266 inches. That all comes up to 1,057 pounds per square inch. And I look online, I find out my PVC yield strength is 8,000 pounds per square inch. So wow, we're looking good because our allowable stress is much greater than our calculated stress. So the way we write this is we write a margin of safety, which is just the allowable stress divided by the calculated stress, that ratio minus 1. We do that because then if we ever have a less than zero margin here, we know we're in big trouble, that we're predicting a failure. Now this margin is plus 6.6. Now that makes you really comfortable, but don't get too comfortable because there's a lot that doesn't account for any strength degradation due to temperature or damage or anything like that. And so if you really want your pipe to burst, you go to 6.6 times that pressure, and that's about 700 psi where that will actually fail at room temperature. The second failure mode we look at is the 1-inch pipe. We're pretty sure this is going to be even better than that, and yeah, it is. We do the calculations. It's only 514 psi, and our 8,000 is much more than 514, so our margin of safety is 14.6. Again, not accounting for temperature degradation in the PVC. This is our barrel, assuming that the pressure 125 psi got clear around here and stayed there. Maybe it is pretty high behind the ball. So here's our calculation. We come up with the pressure, the radius, and the thickness of that barrel. and we get 715 psi. That's still a lot less than 8,000 psi. And we calculate our margin at 10.2 positive. So that gives you a good feeling too. Now let's take a look. This is, I did take a look at the threaded connection between the 1-inch pipe and the 4-inch end cap. And I don't like this because there's not many threads here. You maybe 4 or 5 threads, which is really kind of being a little risky about it. I wish I'd stayed with the reducer concept that the first guy had. But this is how you'd calculate that. You'd say, okay, the pressure's on this 1-inch diameter circle, and it's held in shear by these teeth. Without going this in too much detail, well, it's really weird. I couldn't find the shear strength of PVC pipe online. I found all the other properties, but I could not find the shear strength, which seems strange. I don't know why that would be. From this OD, this is the cement that you put PVC together with. It has a shear strength after 72 hours of 900 psi. So I figured, well, the cement's got to be stronger than the PVC in shear. And so I was able to calculate a margin of safety that's fairly high. 900 is the capability. 191 was the force, the shear stress on that bond line in a 1-inch circle. And I came up with a margin of 3.71, which is pretty good. What if you dropped it? What if you were bending it or something like that? That could easily go much lower than that, and you might have a dangerous situation. So I may remake this, and I would suggest not doing the threaded connections, but do the reducers and the bonded connections, which are much stronger. Here are the Schedule 40 PVC pipe dimensions. This is where I got all this information from my 1-inch, 2.5-inch, and 4-inch PVC pipe. There's another way we can write the margins on this, and we did it to the stresses. Here, turns out online at these websites, they've quoted the American Society of Testing Materials, this particular specification, and they give you a maximum water pressure and a minimum burst pressure. Burst pressure, what we've been talking about so far. My 4-inch burst pressure is 710 psi. The people who sell the pipe don't want you to ever get near that kind of a pressure, and so they publish a maximum pressure of 220 psi, which is fine for us because we only maximum at 125. So they understand. They don't know what the temperature is when you're using this pipe. You could be outdoors on a 110-degree day, and there's a significant degradation in strength, and they don't know if it's beaten up. They don't know a lot of things, so they have their own way of putting a margin of safety in there and saying don't put more than 220 psi in here ever, knowing full well that if it was a pristine room temperature day, you could go to 710 psi before it actually explodes. But before it explodes, there's going to be a lot of deformation, permanent deformation, and so your air cannon's not going to look the same if you pressurize it up anywhere near that. So don't do that. This is just a graphic representation of what they have online. That's a 4-inch pipe, a 2.5-inch pipe, a 1-inch pipe, and this is the burst pressure versus the maximum operating pressure. And you can see, lo and behold, the smaller the radius, the more capability it can take. So that's interesting. So now we can write a margin of safety on those pressures, allowed pressures. And we say it's the same thing, allowed pressure versus applied pressure, that ratio -1. So our margin of safety, if we use the burst, 710 psi divided by 125 -1, still 4.68. And of course, if we use the recommended maximum operating pressure, that would be about a margin of safety just under 2. And but they have a lot of safety in that. And so that's kind of how you take a look at things. There's another way. If things get complicated, the geometry gets complicated, you can use a finite element model. My Autodesk Fusion 360 program, which is free for a startup making under $100,000 or a hobbyist or a student, you get a free license every year if you renew it. And that is amazing because not only can you do computer-aided design, but they have a simulation analysis component in there, and you can do all kinds of things with that. So very briefly, a finite element model is where the program breaks up your part into a lot of little pieces. That's why they call it finite element analysis. These pieces talk to each other mathematically, and they transfer loads and things. And you can imagine if these are there's lots of different loads coming from one to the other, and every one of these 1,500 elements is talking to its neighbor about what loads are locally going through it. That's a lot of computing, lots and lots of equations, tens of thousands of equations just for this one little model. But luckily we have computers, and my computer can analyze this in about 2 minutes, I think, something this size. Bigger computer, of course, go faster, but this is plenty good. So I modeled this PVC pressure chamber, and lo and behold, yeah, the cylindrical part has higher stresses than the spherical parts at the end. By our equations, twice as high as this, and that looks about right. I won't go through the details of this whole finite element modeling, but basically I get 1,161 maximum pressure here and it doesn't show the direction, but I know it's in the hoop direction there. I loaded it with 125 psi internal pressure. Finite element models are very useful. This one, yeah, I kind of knew the answer anyway, but in more complicated, if you have a lot of load cases, if I had a point load here, or I had more complex geometry, or I had inertial loads, if this was being carried in an airplane and sometimes it was being thrown up, sometimes it was being thrown down, and sometimes it was different pressures and different temperatures, I'd have thousands of load cases. And rather than build thousands of pressure vessels and apply these loads and test them, I can do that work with a finite element model. And so once a new design or a new fabrication method, you make something out of that. Once you have some initial testing and finite element work done so that the finite element analysis is calibrated to reality, you feel a lot better about, okay, now we can do design changes, and we know we're very sure we're getting the right answers to this. So you can optimize the design. So since this is not getting as much stress out here in the spherical part, although it's the same thickness, obviously you could save weight, which is very important in aerospace, by thinning this down out here. I could have these parts thinner, and I would do that and then iterate. Analyze it again and thin it out again and analyze it again. They in fact have programs that will do that automatically and optimize your design based on a finite element model. So finite element modeling can save you a lot of time and money down the road in analyzing a lot of different load cases, in optimizing a design, and you can save this and know that the next time you have to analyze something like this, you have confidence that you can do it right. So that's a brief introduction to finite element modeling. This is a little video output from the Fusion 360 program that is showing in steps how the pressure gets higher up to 125 psi, and yeah, my stresses are actually getting higher. So that's another verification that another verification that we're doing this right. You'll notice that all pressure vessels want to be spherical, and if you take a look at the lunar module and the Saturn V, if they can't be, if volume constraints mean that you can't really have spheres, in other words, you could build a rocket and the optimum structure would be just a bunch of spheres attached to each other on top, but that would create a lot of air drag, and so they compromise and they say, okay, the next best thing to a sphere is a cylinder. There are spherical heads. This is the upper stage. This is the first stage of the Saturn V that went to the moon. There's spherical pressure bulkheads on the top and bottom of both tanks. I think this is liquid oxygen. I think this is kerosene, and but it's pressurized. And you can see when they get out in space, you don't have any air drag. And so you really want all of your pressure vessels to be spheres. Probably the reason that they made some of these a little bit cylindrical is because they didn't want to make the lunar lander any bigger than it was, because then it would have to fit. The payload shroud on top of the Saturn V would be bigger. And so they do a lot of optimizing. This is the size of a man compared to that rocket that took men to the moon. I talked about temperature very quickly. This is a chart I found at this website, the PV strength degradation with temperature. We know that at above 100, above 75 degrees, these plastics, they degrade. They aren't nearly as strong. They get soft pretty quickly. So PVC here, there's some other plastics for comparison, but the PVCs we're interested in. At room temperature, we have 250 psi pressure rating. And if we get up to 110 degrees Fahrenheit, which you could on a hot day, have them sit out there, then the pressure rating is only like 140 psi. So that's a huge drop. And that's why we shouldn't be too happy. We had a margin of safety of 6 earlier on. But when you account for temperature that could happen, I took that ratio, 140 over 250, 710 burst pressure divided by our 125 psi applied pressure, and at 120 degrees, our margin has gone from 6.6 down to 2.18. So that's still positive. It's still good, but that's the effective temperature on PVC. I found a couple of videos online of people testing PVC pipes. This is Crazy Builders at this YouTube thing, and they were actually pressurizing this pipe to a certain pressure and then dropping a steel weight on it, and they had it in a box and they had face masks on and stuff. But that's really kind of a dangerous thing to do, because PVC, when it does shatter, it can shatter what we describe as brittle. It just shatters all over the place, and little shards of PVC go flying. The only way to do this safely, relatively safely, is with pressurized water in a water tub like these professionals are doing down here. And lo and behold, look at this. It's kind of an axial crack there that happened when they pressurized this 6-inch PVC pipe to failure. Worse than using air would be using half water and half air, because you basically made a rocket. And if it can really seriously hurt somebody, a rocket or a bomb. So don't ever do that. Very briefly, the fracture toughness of PVC degrades quickly with lower temperatures. So it's important, if you dropped your pressurized cannon on a rock and it hit the pressure chamber, it's a lot more likely to explode. In my view, all PVC projects should be painted soon after fabrication, because another problem with PVC and all polymers is that they degrade in ultraviolet sunlight. Ultraviolet radiation is part of the sun's radiation. You can't see it. It's not light you can see. It's radiation you can't see, but it does affect polymers and make them much more brittle over time. I also design and build backyard roller coasters. I've taken pipe. I don't use the white plumbing pipe. It is not as its fracture toughness is even lower than the electrical conduit PVC. So I took a bunch of PVC pipes and put them in my yard for 2 years. Some of them painted, some of them not painted. And then did impact testing. So I drop a 10-pound weight from maybe 110 inches, and I get 110 inch-pounds as maximum. It's really interesting, because if you test it with 1,000 inch-pounds, it just bounces off and nothing happens. But if you increase it by 50 inch-pounds, just a little bit, all of a sudden it just shatters like this. Hard to see because my piece of steel ran into my camera mount. So this is, so in other words, if this was just a little less of a height of a drop, nothing would happen. It just bounces off. But this is how you can do that. Now, what I found was without paint, the PVC fracture toughness degraded over 2 years in my yard by about 50%. The painted PVC degraded by only less than 5%. So really hardly any degradation. So I would, anytime you're going to have something PVC under stress and you want it to last a long time, especially if you're going to be outside, then you want to paint it, preferably with a dark paint because that blocks the UVs better. One little thing at the end, I won't go through the physics of it, but I wanted to see how fast and how high my tennis balls were shooting. There's some physics calculations that aren't too hard. You can look up elsewhere, but basically by counting the seconds that it's in the air from the time it leaves the gun to the time it hits the ground, I can estimate the velocity. Like they were my first ones when I pressurized to 75 psi, it was taking about 5 seconds to go up and come down. The velocity is 80 feet per second, or about 55 miles an hour. At these speeds, the air drag is not too severe. If you go to much higher speeds than that, if once you get above 50, 60, 70, 80 miles an hour, that velocity, the drag increases with the velocity squared. So remember, we take a look at equations and we see what's really important about an equation, and that's when you see that. You see something squared, it's more important than something that is not squared. And something goes to the cube or to the fourth power, there's even more sensitivity to your results. So we know this, cars get pretty good gas mileage under 55 miles an hour, but if you're going to drive 70, then all of a sudden you're using a lot more gas. That's because the air drag increases with a square power. The maximum heights by this physics equation, and I'm getting for these 75 psi shots about 300 feet. And that seems pretty reasonable. To make it easier, I ran that spreadsheet a bunch of times, and so I have this thing, and if I count the number of seconds, either 1001, 1002, or do it with my stopwatch on my cell phone, I can get 4, 5, 6, 7 seconds, whatever I get, and then I can easily see, okay, the speed is about this, and the height that I went up to is about this. In conclusion, appreciation to Autodesk Fusion 360 Computer-Aided Design Program. It's free for students, hobbyists, and startups making under $100,000 a year. You have to renew the license every year and tell them you're not that you're one of these things. It's a great way to get started for real computer-aided design, not just something that makes fuzzy things like some of the programs out there. But this is highly dimensions. It has a lot of great capability. There's great tutorials online. It's a great way to start. I'll cover the benefits of that somewhere else. And also to the GrabCAD guy named username Bale, where I got the model, and he got the idea from antennalaunchers.com. So that's my engineering assessment of an air cannon. Thanks for listening.